Good afternoon, everyone. Welcome to the Neil Graham Lecture in Science here at the Paul Cadario Conference Center. My name is Sally Tagliamonte, and I'm the acting principal of University College. I'm also a professor in the Department of Linguistics and a Canada Research Chair in Language Variation and Change. Let's come together on this auspicious occasion with intellectual curiosity, openness to new ideas, and a common goal to learn more about the universe. But before we look to the stars, I would like to begin with the earth under our feet. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Mississaugas of the Credit and the Seneca. Today, this meeting place is still the home to many Indigenous people from across North and Central America, a region of our planet called Turtle Island. We are grateful to have the opportunity to work on this land. I ask that you take a moment to reflect on the Indigenous histories of the land upon which you live and work from wherever you happen to be this afternoon. We have many people online listening in. The Graham Lecture was established through the generosity of Mr. Neil Graham, a 1930 graduate of University College who had been a high school mathematics teacher, a predominant skill that our speaker excelled at, even in high school as a student at Jackman Collegiate, just down Wesley Street, as well as in her undergraduate program here at the University of Toronto and a student at University College. We are extremely honored to have Professor Sara Seager back here with us. Professor Seager is an astrophysicist and professor of physics. She's also the class of 41 professor of planetary science and a professor of aeronautics and astronautics at the Massachusetts Institute of Technology. Before we introduce Professor Seager, I want to give you some quick housekeeping notes. For those attending in person, a microphone will be passed around during the Q&A portion of today's lecture. Please raise your hand and to ask a question once the lecture concludes. Please speak into the microphone rather than speaking without one in order for the audience online to hear your questions. For those of you attending virtually, live closed captioning is available for this event. The option can be turned on simply by clicking the closed captioning icon at the bottom of your Zoom screen. Please use the Q&A function to submit your questions. I am now going to call upon Christian Menou, Associate Professor, Department of Physical and Environmental Sciences, University of Toronto Scarborough, to introduce our distinguished speaker. Christian?
It's a great pleasure to introduce Professor Seager for this lecture and tell you a little bit about our career trajectory, I guess, which I've witnessed firsthand. Professor Seager has had a really groundbreaking career in planetary astrophysics, and you could argue that's a field she initiated as a PhD student at Harvard. Her contributions have many firsts. I will cite and give you a few examples of what she's done. She put forward the first models of exoplanets that we now call hot Jupiters under strong irradiations. She was the first to study the emission from such planets, leading to the first actual detection of their atmospheres. She also was the first to study polarization from the emission of these planets, their oblateness, using their oblateness to infer properties, photochemistry for exoplanets, etc., etc., etc. Many, many, many firsts. In short, she's been really leading the field of exoplanet studies towards various breakthrough discoveries and measurements. And for all these contributions, she's been the recipient, she's been awarded a great many awards, of which she asked me not to include the complete list because there's so many of them. So I'm just going to highlight a few. She received the very prestigious Sackler Prize in Physics, MacArthur Fellowship, and most recently, the Kavli Prize in Astrophysics. These are major international awards. She was elected a member of the US National Academy of Sciences, and she's also now an officer of the Order of Canada. So this is a lot of awards, very well deserved, and we are very fortunate to have her here today to tell us about the search for signs of life beyond Earth in the new space area.
Thanks, everyone. This story begins billions of years ago when the first simple single-celled bacteria called cyanobacteria did something very clever. I don't know about you, but I don't usually think of bacteria as being clever, like the mold in your fridge or something like that. But this life form figured out how to harness energy from our environment, photosynthesis, and in the process generated a waste gas, oxygen. This gas, oxygen, eventually filled our atmosphere. And so this humble life form re-engineered our atmosphere. But it took time. Over billions of years, this oxygen came to be. Now, we all rely on oxygen. But what you might not know is that without life right now, without plants and photosynthetic bacteria, we would have virtually no oxygen. And so because oxygen has to be continuously replenished, it's highly reactive. It wouldn't be there without life. So I love to imagine an intelligent civilization on a planet orbiting a nearby star with the kind of telescopes we're hoping to build. And if they look at our planet, they're going to suspect that there's life here. That's not by things like the Great Wall of China or by pollution or city lights, all the things we think are very sophisticated. No, it's going to be because of this simple life form, and plants today have generated a gas. So are you with me? Because that's the whole idea about finding signs of life beyond Earth, is that we're going to study exoplanet atmospheres, and we're going to look for gases like oxygen or other gases that shouldn't be there. They're just highly reactive, yet they've managed to accumulate. They must be continually produced. The analogy I almost forgot to mention is it's like the perfume bottle. I don't know if people still have perfume bottles these days, but if you open the perfume bottle, the smell kind of makes it across the room. But if you close the bottle, the smell goes away because the molecules are reacting and they eventually dissipate. And that's the same with these gases. And by the way, there are a few astronomers in the room, I know. Did you know that this idea about searching for signs of life by gases with telescopes has been around for almost 100 years? And it was the renowned astronomer James Jeans who wrote about this. And he's the other things he's famous for, but he has a textbook, and there's like literally one paragraph. He talks about oxygen and looking for oxygen on Venus and not finding it, having an upper limit, let's say, and saying, well, there's no intelligent life on Venus because we intelligent life need oxygen. So there you go. Now, the reason why partly I'm here and we're all here is because we're at a milestone in human history for searching for signs of life, because we have a new telescope called the James Webb Space Telescope. Just to see where you're all at, how many of you have heard of this telescope or have followed it? Okay, because you're mostly space enthusiasts. Well, that's why we feel like it's our first ever chance to find signs of life. So we're going to do a deep dive here, and I'm going to try to, throughout the 45 minutes or so, give you stuff you might not hear anywhere about why it's so hard, what we're doing, and what our kind of hopes and dreams are. So it starts with this called a transiting planet. Some of you know this, some of you don't, but do you see the little planet going in front of the star? We don't spatially resolve any stars like that other than our sun. But that's an artist's conception. But what we do see is the bottom graph. So the star is just shining on its own, just happily shining. And when the planet goes in front of the star drops by the characteristic shape. And it is basically the planet area compared to the star area, like pi r squared planet over pi r squared star. And this is for systems that are fortuitously aligned. They happen to go in front of that star as seen from our viewpoint. And there are thousands of planets we know of that do this. There are probably millions more. And there's many we don't see because they're not transiting. But for these planets, they're very special because we're able to study their atmospheres of some of them. And that's what I'm going to talk about next. So on the top, do you see the picture, the artist's conception of the planet, and see the atmosphere? It's all very exaggerated. But there'll be this drop in brightness due to the planet going in front of the star. And this is showing you the relative brightness. In astronomy, we just make it simple. We normalize it to 100%. So the star is at 100%, and it drops down by a few percent depending on the size of that planet. And that is real data taken with the James Webb Space Telescope. What's funny is this data looks way better than the cartoon I showed you. The cartoon was pretending there's like noise in the instrument or in the star, but wow, that is like, you couldn't imagine a better transit light curve. It is just wow. Well, the concept of the looking for an atmosphere, and I really want you to get this, because this is, if you could just learn one new thing or take away one thing, it's how we study, one of the main way we study atmospheres. And that is here. You can see that if we're just looking at the planet without an atmosphere, it has a certain drop in brightness corresponding to that dark part of the planet compared to the star. But when the atmosphere is present, the planet looks a tiny bit bigger. And we're using this principle that the atmosphere doesn't absorb at every wavelength. Some wavelengths the atmosphere is absorbing, others it's not. So if we could observe this planet at all wavelengths, if the atmosphere is transparent, the planet is a certain size. And if the atmosphere is opaque due to a lot of absorption, the planet will be a little bit bigger. Are you all with me on this? Because we're going to get to try it now. Here's real data from the James Webb Space Telescope. This is relative brightness. Now it's normalized to 1. And time from mid-transit. So this transit's lasting a few hours. The black line is like the best fit to all the data across all the wavelengths. So the black line is kind of like the average. But what the colors are, they are the transit measured at different wavelengths. So your job is to see if the planet looks a tiny bit bigger in one of these colors or wavelengths. And if it does look a tiny bit bigger, it means that's where the atmosphere is strongly absorbing. Does anyone see it yet? I just want everyone to be able to see it. So let's let it run a bit. And if you're coordinated enough, see the little W running by in the top right corner? That's wavelength in microns. These are like infrared wavelengths. So now your job is to see where it drops. Where do the points drop down? Where is the planet a little bit bigger, blocking out a tiny bit more light than other wavelengths? And now you can shout out a number if you can coordinate and see where that is. 4.4, I hear 4.7, 4.5. So you all see this drop, and wow, let's let this land. By eye, you have seen signs of an exoplanet atmosphere, where this planet looks a tiny bit bigger because the atmosphere is strongly absorbing. Well, you're not looking as impressed as I would have thought. You're impressed, okay, you're impressed. I mean, this is such wonderful data. It is absolutely astonishing. And we're all very, very thrilled with this. Well, I do have a few graphs, so if you're not graphically oriented, you don't have to understand these to understand the rest of the talk. But what we do is we're measuring the fit to this data. What is the actual drop in brightness, like 2% or 2.1% or 2.0003%, and we plot that on a curve. So now you're looking at the amount of light blocked in percent. So the whole, remember the dark part of the disk is blocking about 2.1%, and where the planet looks a tiny bit bigger, I heard 4.3, 4.7, yeah, it's all right. Between about 4.3 and 4.5, see that rise, the planet's a tiny bit bigger. It really is just like a tiny, tiny bit bigger, like 0.1%, very small. And that is bigger. Now, if there was no absorption as a function of wavelength here, this would just be a straight line. And the points with the error bars, those are the real data from the transit light curves, and the blue is the best fit. So basically, yeah, if you agree with me, this is different from a straight line. You are seeing signs of an exoplanet atmosphere. So one of the reasons I got all those awards Kristen mentioned is because I invented this idea. And I wanted you to know that at the time, this was back in the 1999, 2000, it's like I put the idea out there, and 2 years later, some astronomers observed it and found the first ever exoplanet atmosphere. But at the time, that actually wasn't considered a big deal. It was considered like cute, like I was applying for jobs to become a professor and I couldn't get a job because people just said, well, it's a good idea, but this is the phrase, a one object, one method success. Meaning that although someone used my idea and found the atmosphere, they thought the field would peter out, that there were not enough bright host stars, that we would never find enough transiting planets. And in one place I interviewed, I was just taken, you go into a one-on-one meeting and this professor just said, well, there will never be very many transiting planets. But at the time, I was also working on trying to find planets by this method, the transit technique, by looking at thousands of stars at one time. And if you're working on it, anything you're doing now, like whatever you work on in your own world, you know how close or far you are from getting it to work because you're like literally working on it on a daily basis. So I knew we were really close to unleashing like a floodgate of transiting planets. We just had to get, we were figuring out the strategy and the software, not just me, but others. So what can you say to that? Like you literally don't just say anything. But a decade or so later, I returned to that same institute, and great, the professor was on my list of people to meet. And he's like, oh, welcome. I always knew this would be a big deal. And I was just like, get me out of here. So now, this transit transmission spectra, as we call it, it's a big field now, and hundreds, maybe 1,000 or more people work on it. We would say a quarter or a third of all James Webb Space Telescope time have something to do with exoplanets. And for my talk today, I'm not going to go through all the details. I just put up some pretty pictures here. Sometimes for the public, we'll say, just to make you laugh, squiggly line science. But you're seeing lines, you're seeing atmospheres. There's a lot of planets out there. And there's just so much going on, it's nearly impossible to encapsulate it. But the point is, we are observing planets. Most of these planets, they're not small rocky worlds of the kind that might host life. They're easier to study. They're big giant planets. They have puffy atmospheres and they have very strong signals. I have a little bit of a confusing plot, but just give me a moment while I walk through this because I'm going to move on to space and gases, but I wanted to just encapsulate for you all the kinds of planets out there. There literally are, this is a plot showing you the size of the planet on the y-axis, 1 through 10 through 20 times Earth radius. On the bottom, it's showing you mass in terms of Earth masses, but that's spanning a ginormous range, thousands of masses. And every point on there is a planet. It's a known exoplanet with a measured mass and size. So you can just aesthetically look at like how many there are. And this is a small subset of all known planets. There are thousands of planets, and this is maybe like, I don't know, 700. But what you can see is that these planets cover like literally all masses and sizes, right? And also all orbits. And it's so incredible, really, that nature gave us not just distinctive planet types, but literally a full range of all kinds of planets out there. So I wrote on there, we're studying big planets that are hot and big and puffy, and they're too hot for life. We're trying to get to these smaller and smaller planets. And lots of people are trying to work to not just find these planets, but try to study their atmospheres. So just because of all this, I do have a phrase I really like, because when I started exoplanets, hardly anyone worked on it. People thought it would go nowhere. And today it's a booming field with so many planets and everyone loves it. I like to say that in exoplanets and the search for signs of life beyond Earth, the line between what is mainstream research and what is crazy is constantly shifting. And because of where we are now, myself and others, like we're emboldened to do the crazy because now this is mainstream. So we have to keep shifting over. And so we're going to come back to a bit more of that in a moment. So yes, do you want to ask a quick question? Which one am I from? Yeah. So what I'll talk about today is I'll just talk about some gases. I'm going to tell you like our biggest hurdle in trying to find signs of life beyond Earth, and then how we can make through this main hurdle. But do you know it's not just oxygen, but life on Earth produces thousands of gases, like that mold in your fridge, or if you have a compost, or if you go to a swamp and it smells really bad, or like the pine forest that smells great. Those are all gases being produced by life. And it turns out that on our Earth anyway, oxygen, although it was started by life a few billion years ago, it took a long time to accumulate to these big levels that we can detect from afar. So there could be a life-bearing planet out there, but maybe it's not generating oxygen. So there are so many gases on Earth, it's not just oxygen, but I uncovered this little factoid, thanks to a great question about our own atmosphere. It turns out that every gas in our atmosphere to the part per trillion level, so trace gases, with the exception of the noble gases that are not reactive, every gas to the part per trillion level is actually made by life, even though they almost all have a dominant source that's not life. So ozone, for example, it's made from oxygen, but by photochemistry. But actually, you know what? It supposedly is actually produced inside some cells. And of course, you don't have time to fact check me on this, right? So you're just going to have to believe it. But you could literally check it later. It's crazy. Any molecule you could think of, like, I've listed just a few of them here. I kind of ran out of space and motivation to like put them all on the same slide, but there's a lot of them. So partly because of this, when I was about like a decade or so ago, I was trying to think of what are the gases that on another planet might accumulate. I came up with an idea, a kind of crazy theory. Now, how many of you here are scientists, or even if you're not, how many of you receive emails about crazy theories? If you're a scientist, you do actually. People email you, like in astronomy, they'll have a new theory of gravity. In exoplanets, it's UFOs. People have evidence of UFO. Every field has that. But how many of you have had a crazy theory? But please don't send me your crazy theory, okay? Well, I had a crazy theory. I wanted to say, you know what? All these gases made by life, maybe every single molecule that's a gas at room temperature and pressure, maybe it's all made by life. So I went off on this giant journey. It's like, you know, the squirrels gathering nuts at this time of year. Like, they don't necessarily know why they are. They're gathering way too many, right? Too many. I just went out, and this was about 10, 15 years ago. I learned Python. I made like a combinatorics code where I took the most important elements and put them together in every way they could. I learned how to scrape websites. That's where you gather all the data with your computer, not by clicking on things, about which of these molecules actually existed in real life, because you can have a structure like a name, and there's many physical incarnations of that, thousands of molecules. I recruited 2 biochemistry friends. We got this giant database. Well, where does the professor go with the crazy theory? We have to go one level up to the Nobel laureate. And there's a Nobel laureate in our field, Jack Szostak. He doesn't work too far away from where I do. And I asked him, he's the one who told me, okay, that there's ozone made inside some cells when I first mentioned this idea to him. So I thought I could go, and my biochemistry colleagues and I, we got our presentation together. We went across the river, took the subway, one stop, went to talk to him. And he crushed the theory by a single counterexample. So it's really neither here nor there, but the point is to encourage everyone to, explore. Like, that's what science is. It's a journey of exploration. And we went on this journey. We literally have the most exhaustive database of all molecules in gas form at like habitable conditions, also tied to every life form. Okay, you're wondering why we're doing this. Every life form that makes it as well. And we found some incredible things that is a bit like different from here, but we calculate the sea of molecules that populates what's called chemical space. And we created algorithms to filter them, partly so we may be prepared to recognize biosignature gases of every kind. But we also found that some molecular fragments, they're literally never made by life, like they're avoided, even if they're extremely commonly made in industry. And this is a sort of separate thread that we're following. But I mostly told you this story because we do really think on another world, we don't know what gases could accumulate, and we want to keep an open mind. So just to kind of finish up this part of the story, I just wanted you to see this cute graphic that my grad student and I made, but we don't want to miss it. In exoplanets, we don't have a million planets to look at. We want to make sure we're prepared for any gas. So we have a triage and an evaluation phase, and I probably don't need to go into the details. You can just appreciate there's some flow chart, there's something we do. But I did want you to know the most important part of this kind of evaluation. It actually is photochemistry, because all the gases that are made, just like the perfume bottle idea, they get destroyed and they react away with the environment. And actually, the main thing that's really going on is the ultraviolet radiation coming from the star, or in our case on Earth, coming from our sun. And that radiation destroys molecules, either directly or it's creating OH. It's a radical, and it is like literally known as the garbage eater of the atmosphere. And this gas just kind of reacts with everything there. So I just have this like picture of an atmosphere saying why it's so complicated. We have equations to describe it in detail, but basically there's like volcanoes, and there's life-making gases, and there's photochemistry that comes in from the star and alters it all, and then some gases escape our planet. So it ends up being a very complicated business to evaluate everything, and thinking of gases and which can accumulate, how do they get destroyed, do they have false positives? So we do have like a very distinctive way that we do this, and other people do similar things. We have to ask ourselves that's what the little flow chart is, but I'll explain it to you. We ask ourselves, like, how much gas do you need to accumulate? Or how much gas in the atmosphere do we need to make a signature we can detect from far away? And then we have to ask ourselves, how much has to be continually produced in order to fill the atmosphere to that level? So let's say we pick a gas, we need 1%. That's really high, but 1% of our atmosphere. We need to know, how much do we make? Do we have to make like 1,000,000 times more than the oxygen production rate? We're doing a kind of reality check to see if the gas we are trying out as a potential biosignature, if it's really physically viable to be there, or if there's just some crazy rate that has to be made. That's like, you couldn't, I don't know, maybe you could, but you couldn't imagine a planet with trees like 500 kilometers tall. Too much. I'm just saying we're trying to figure out what the rate limiting factor is. So we do, and others, we just evaluate like all gases. I just put a bunch of gases here. And we're just trying to ask ourselves simple questions like, for a gas, does it have a spectral feature, like a unique spectral feature that can be discerned amongst all the background gases like carbon dioxide or other things? We ask ourselves, is there a reasonable production rate required against how fast it's being destroyed? And most importantly, we do want to know if there are any significant false positives. Like, I'll give you an example. Carbon dioxide, we all breathe out carbon dioxide. So that is technically a wonderful biosignature gas because we're producing it in large amounts. But carbon dioxide is already here. It's already been vented out from volcanoes and it already makes up a large part of our atmosphere. So carbon dioxide, it's a terrible biosignature because it's already there. There's like already a sign of it. So we kind of go through this list of gases, and I just wanted to highlight one of my favorite gases we studied, and it's called phosphine. Has anyone heard of the gas phosphine? Like literally, unless you're following space science or you're working on pesticides, you probably have never heard of phosphine. Because on our planet, we all need phosphorus. It's part of our DNA and our biomolecules. But because our Earth has hardly any hydrogen, we have mostly oxygen, phosphorus combines with oxygen to make molecules called phosphates. It's very hard to make phosphine on Earth. It requires a lot of energy. It wouldn't just come out of a volcano because there's almost no hydrogen and it requires lots of energy. Phosphine on Earth is only associated with life. It's associated with bacteria in oxygen-free environments and with us humans. I really like phosphine. I have a little chart on it for you. And the astronomers here, you can look at the chart. It's showing you the cross-section, so how strongly phosphine absorbs at which wavelength. And that's in white, and then the colors are just other assumed background gases like carbon monoxide or carbon dioxide or water. And you can see the white is like peeking out here and there. It has unique spectral features. It can accumulate in the atmosphere, and it doesn't have false positives. So phosphine is one of the gases I just wanted to highlight for you for a moment. So really strange thing, so phosphine is a gas. There's lots of options. It's all kind of like a theoretical exercise until we get data. But there are the gases. So far, I've explained to you, all very briefly, of course, we have an established way to study atmospheres today using the transmission spectra that we all got to see for giant planets. All right. We have some known rocky planets. I didn't talk about it, but I flashed up that chart that had all the, so many planets. And we have some planets of the right temperature to host life. And we have a list of potential gases. So that's kind of where we're at. We're working on this hard, and so it sounds like we're in a good place, right? Well, we definitely have a problem. And this problem is something I got onto completely by mistake. Here I am, an astronomer, although I have 2 or now 3 biochemistry colleagues. Well, another astronomer halfway across the globe was also working on phosphine as a potential biosignature gas. And she didn't have those biochemistry colleagues, so to her credit, she dug through the literature and found some papers on her own. And she wanted to search for signs of life on Venus, our sister planet. Now, in astronomy and many sciences, we sometimes reserve, it's like, if you're going to splurge on an expensive item, or maybe you're going to just have that food binge on some like really yummy dessert. We also splurge on some time spent on a crazy idea. Remember I told you the line can only shift if people are going to invest in crazy. And for whatever reason, she wanted to search for signs of life on Venus. And she decided to look for phosphine because it's only associated with life. Remember all the reasons it's a good biosignature gas. And also, phosphine has a it's all molecules rotate, but this one rotates and absorbs energy at radio astronomy wavelengths, and she's a radio astronomer. So someone connected our two teams and suggested, since it was very obscure for astronomers to be working on a gas that most of you haven't heard of, we should work together, and she invited us to join her team. So we joined her team, and long story short, after a lot of really, really hard work, hard data analysis, hard interpretation, and this was in the fall of 2020, we made an announcement of the report of phosphine gas on Venus. And this was super exciting for us. We said we found tiny amounts of phosphine, like at the parts per billion level. We had gone through every process that could make phosphine, like lightning, volcanoes, meteor delivery, pretty much everything possible. And remember I told you 100 years ago, the astronomer said we should look for a gas that doesn't belong. We're like here now after 100 years, and we didn't say there's life on Venus. We just said there's room for it because we ruled out, we wrote 100 pages. I mean, the chemistry isn't all known, and Venus, we don't know huge amounts about it. And this discovery was literally so controversial from the get-go. It was, just for lack of a better word, I know we have like linguists and English majors, but trashed at every level. So I want to tell you a bit about this because let's just say we know a lot more about Venus than we ever will about an exoplanet far away. And this is the hurdle. I'm getting to this, why is it so hard? It's a hurdle. And we're naturally skeptical. We should be, right? Because fake news and everything, and scientists especially, we're trained to be skeptical. So the first question, is the signal real? That's your first question you should ask. And you have to do a lot to the data. The signal's a tiny, tiny proverbial needle in the haystack. And data in astronomy is all public because they're taxpayer facilities typically. And astronomers took the data, analyzed it, and the large majority of them did not recover the signal. Now that's bad news. But we had two separate telescopes. On one telescope, people did commonly recover the signal. So for argument's sake, let's assume the signal is real. Let's just all adopt that for now. The next criteria is the molecule correctly identified? And in that case, phosphine, there's one other possibility. Unfortunately, there is one other molecule, sulfur dioxide, that is known to be on Venus. It comes out of volcanoes, has an overlapping line. We can argue why it can't be sulfur dioxide. It would have to be way too much of it compared to what's measured. So let's all agree now the first two are correct, just so I can walk you through the arguments. If those are correct, now we want to know, is that molecule made by life or is it made by something else? It would be very hard to rule out every single possibility to a level we could everyone in science in the world could buy into. And although I told you we literally had, it doesn't matter, you could write 100 pages on anything. We had 100 pages. Lots of people proposed ideas of how phosphine could be made. One of them, we all traced back, we worked together to trace back to an error in a database on a thermodynamic quantity of a certain set of molecules. But really, it looks like it's nearly impossible to make. So those are the reasons why people ultimately mostly don't agree. There's still controversy. If you Google it and you can read all about it's going back and forth. So two things to tell you. One is that from 4 decades ago, a NASA mission went to Venus and went through the atmosphere and actually has evidence for phosphine. And this is reanalyzed data that's been archived for all those decades. So that's where we're at with Venus. But let's just take a moment, and why is it so crazy to think of life on Venus? Do you know how, we have this thing we call the giggle factor in science. If you have an idea and you tell someone about it and they laugh, sometimes you know how you can't help laughing because it's just so crazy? Yeah. The search for life on Venus, it is until the giggle factor is because Venus is too hot for life. The surface is too hot. There's a massive carbon dioxide atmosphere that creates a greenhouse, and the surface is literally hot enough to melt lead. No life that we could understand could survive on the surface. But just like on Earth, if you hike up a mountain, I'm just remembering how flat my home province is. So it's not a good thing to say here, but if you live in the mountains, you hike up a mountain, it gets really cold. Go in an airplane, it gets cold. So too on Venus. When you go up 50 kilometers above the surface, it is the right temperature for life. And there are clouds on Venus. And our Earth clouds, they have life in them. Bacteria get swept up and temporarily stay in the clouds. But it's not like here where today, the clouds, they're breaking up, they're reforming. Venus has clouds always. 100% cloud cover, 20-kilometer deep clouds, always, always there. And this is why we think that over half a century ago, Carl Sagan proposed this idea that there could be life in the clouds. But life in the clouds of Venus, well, the clouds aren't water, actually. Unfortunately, they're made of sulfuric acid. And this is some people know, I'm really pleased that our UC principal knows about sulfuric acid. It's nothing people normally know about. I think it's generational, because I think today kids are not allowed anywhere near it. It is, yeah, because if I ask people and poll them, people have tried it in their lab, or some people, I don't know why, but they had it in their basement. It's nasty. So yeah, we are here, and I've walked you this far, but we're really struggling here because can we ever claim a robust discovery of an exoplanet sign of life? Given about the whole Venus when it's right next door, and we have sent probes to Venus, the former Soviet Union sent like over a dozen probes. We know kind of about Venus, but an exoplanet will always be unknown to us, even though we're looking for a gas that doesn't belong. This is like literally a career crisis right here. So while mulling this big question over, let's take a mini mental break. So we're going to do like a little side talk here. And I know you're all probably not going to be able to mull it over just because, but you know how if you sleep on something and then you wake up, it's sometimes more, okay. So we're doing the equivalent of that for a few minutes. So one of the reasons why this idea of life on Venus is just so insane, we think it goes back to this demonstration that don't do it now, but later look up on your phone because it's amazing. This picture is, we grabbed it from a movie of a person holding that bottle of concentrated sulfuric acid. And this person is pouring it into sugar, what's like the sugar you'd have in your cupboard for baking, regular sugar. And wow, look what happens to it just after like less than a minute. It essentially gets super hot, it puffs out. It's like, wow. It is, really it's getting dehydrated, but it's just a ginormous, scary mess. And our DNA has a sugar molecule in it. So that's why any of our life can't survive in sulfuric acid, because it has a sugar molecule and it will get destroyed. And so we think that's where this misconception comes from, actually. That, not misconception, but this conception, okay, let's just say this legit concept that none of our life can survive. And I just had this quick story I wanted to say that I started working on Venus because of phosphine, but we decided to do some real experiments. And I wanted to also share with you how I, as an astronomer, got into a new field of chemistry. And this does go back to the pandemic summer. It's a tough thing in the pandemic, but one of our kids was in high school, and there were no jobs for kids, nothing. The sports fields were shut down. The police, like, they'd taken the basketball nets off. Some families, like, didn't want kids to interact. So one of the 17-year-old, I put him to work on just some computer stuff, like online research about materials that could survive sulfuric acid. Well, he finished that in a few days, remember, bored pandemic summer, and he pushed to do real experiments. Well, it turns out you can't order a lot of sulfuric acid to your house, but you can order a lot of little bottles. So we ordered like a lot of little bottles of sulfuric acid, and we set something up outside on the front porch, experiments. Now, if you're a 17-year-old, super bored, nothing to do, we're doing experiments outside on the porch on a summer day, what are you going to put in sulfuric acid? Remember, you're just testing stuff to gain intuition. Coca-Cola? Okay, I don't know if you're going to put Coca-Cola in. Something outside, you're looking around, you're just going to grab something. Leaves and grass, you're very nice. Let's dial back to teenager. Bugs, all right. Well, before I could say, please don't do that, he put an ant in sulfuric acid, and it had a seizure and turned to goo immediately. That wasn't very nice. But it turns out other things did survive, like the rhododendron, the waxy leaf, it survived for a while, then like wax from his braces, pencil lead, graphite, like a lot of things actually do really survive. And fast forward a while, that son went into study biochemistry, and we started to get some more sophisticated equipment. A friend, another soccer mom actually from Harvard gave us she was retiring an old teaching machine that's like a desktop UV vis spectra. So you put a sample in, you shine a light through it, and you can measure what's in your sample. So we started to do some real experiments. And I'm going to now update you. Remember, this is like our aside mini mental break about an astonishing brand new field that I'm so excited to share with you. And this is a radical idea. Remember crazy? We're now on the other side of crazy, the crazy side, that wow, maybe sulfuric acid itself, instead of water, could be a solvent for life. Now, what we did was, with the same said son and my biochemistry colleagues, we took our amino acids, our 20 biogenic amino acids, and put them in sulfuric acid to see what would happen. And you know what? They're actually stable. One's unstable, it's fragile to begin with. Half of them get chemically modified. They are sulfonated or sulfated, like the sulfuric acid gives them something. And there's just like a little tiny picture there you probably can't see, but if anyone here does nuclear magnetic resonance spectroscopy, you'll recognize that little plot. So we would put it in sulfuric acid, and glass, by the way, is stable. So these little long glass tubes, take it to the NMR lab, and then come back a week later and also test it in water. And there's actually 3 overlapping lines there. One of them is, this is for the amino acid alanine. One is water, one is sulfuric acid, and one is less concentrated sulfuric acid. And yeah, they're all lined up. It behaves like stable. We also put, not our DNA is unstable, we already covered that, but parts of our DNA are stable. The latter part, ACGT, those go in sulfuric acid and they get protonated, but they are stable, almost too stable, stable for a year or more. And when we dug in the literature, we actually found evidence that people had worked on that, not for Venus, but just for the sake of chemistry from decades earlier, actually. And so you could have pieced some of this together without new experiments because it existed in obscure, I hope those people aren't here. They might not appreciate it being called obscure, but in what seemed like obscure journals, right? And it's so much more than that. We got some colleagues to try some experiments, and they showed that using simple organic molecules like formaldehyde, in the picture there's a piece of a meteorite, they put it in sulfuric acid, and especially if they heat it, it evolves into a rich organic chemistry. And we're like, wow, we're planetary scientists thinking that sulfuric acid just is sterile to any interesting chemistry. And they did a bit of not too much research and found that the oil industry already knew about this because they use concentrated sulfuric acid to take organic products to more sophisticated organic molecules. And this evolves all the way from a simple molecule to like a ringed molecule. Lastly, and this just made it onto the archive, we had some other colleagues take lipids with a polar head and put it in sulfuric acid. This is copying experiments people do to try to create life in the lab. They take these lipids, put it in water, and the polar head points outward, making a little tiny spherical vesicle, like a poor person's cell membrane. I'm not going to say it's a cell membrane. It's not a cell membrane, but it's like a start. And we put these in sulfuric acid, and they formed that little spherical vesicle. So this field is amazing. We're recruiting other, you can tell how excited I am. We're recruiting others to do experiments. And we're trying to make like a DNA-like molecule, not our DNA, but an informational polymer by swapping out parts that is stable in sulfuric acid. So I can convince all of you, not that there is life on Venus, but that it's worth going to Venus to find out whether or not there's life. And that's what we're doing, actually. We're going to go back to Venus. And I'm proud to lead this consortium of a series of astrobiology-focused private-public partnership missions to Venus. And in here, there's like a picture of what one of our missions might look like. But when in my talk, I called it the new space era. This is what's going to make this possible. It's the lower cost to space. There's actually smaller rockets than there used to be. And these small rockets you could get for yourself. And you could send miniaturized, like we have sent many missions to Venus, not us, but NASA, the former Soviet Union. But now things are miniaturized, there's more sophisticated equipment. And we're aiming to kind of shake up how we do space science, not waiting 4 decades like we have to go back to the atmosphere of Venus, but to try to send more things, building on what the commercial space world is doing for us. And we do have our first mission to Venus. We have a private-public partnership. It's actually mostly private, actually. You can ask me about it more in the Q&A, but it's a Rocket Lab mission to Venus. And I thought I would just try to tell you a tiny bit about this mission. First of all, it is a really simple, cheap mission, almost the simplest thing you can do. It would be like one of the team members, I don't necessarily like what he says, but he says it's like throwing a rock at Venus. It's a rock with equipment, but it has no parachute. It's not going to be a balloon. It's going to rush through the atmosphere. This is showing you time from entry on the bottom and altitude on the y-axis, and it's showing the little probe. It'll hurtle down, and it'll just slow down due to drag. So by the time it gets to this cloud layer that we care about, it'll spend 5 minutes in the clouds. And we have only been allocated like 1 kilogram for our instrument. And it's like, imagine like a series of Russian dolls. There's a rocket. Inside the rocket is a spacecraft. That spacecraft goes to Venus. Inside the spacecraft, there's a probe. And inside that probe is a pressure vessel. And inside the pressure vessel is our instrument. So here's a sort of cartoon mock-up of the probe. It's not very big. Our probe is made, it exists. It's getting a heat shield attached to it now at NASA Ames. It's about like this big, it's like 40 centimeters across. And it's just showing you, I'm not gonna have time to go into all the detail on here, but it's showing you some of the schematics of what's inside. And that blue arrow on the right is showing you like the focal distance, 20 centimeters out to where our instrument will shine a UV ray, a UV light laser out into the clouds. And it's going to probe those cloud particles. The first thing we're gonna do is look for autofluorescence. There's a picture of someone getting a test. You know how that will jog your memory, like a nightclub or a funhouse for kids, where things light up if they get an ultraviolet light because it's exciting electrons, which then have to drop back down and re-emit energy. It turns out that organic molecules, like think of a ringed carbon molecule, the electrons are shared in such a way that they're quite loosely bound and they're very easy to excite. And the goal of this fluorescence experiment is to see if there are molecules fluorescing that might indicate there's organic particles in sulfuric acid. And that's, on the right, it's just some laboratory experiments we did to show where should our laser be, what wavelength, and what wavelength should our detector be at. Yeah, I'm gonna just go through these a bit quickly, but the other thing we're doing is we're measuring the backscattered polarized radiation. You know, no particle in nature scatters equally in all directions. For example, water vapor, you know how you see a rainbow on special occasions because it's bunching up the light. But it turns out encoded in how a particle scatters radiation are properties of the particle. So we're measuring backscattered polarized radiation from the UV light that we're shining out, and we're going to try to constrain what the particle is made of. It's a bit ambiguous. And there's you make several instances of instrument, but on the right, they're the flight and the flight spare, all the parts all laid out from a while back. So that's the mission to Venus, but I couldn't help sharing you. We're very ambitious, of course. And after this first mission succeeds, we want to send a balloon mission to Venus, not just to get an idea what's there, but to bring a mass spectrometer and actually identify molecules complex enough that people can agree that they are made by life. And guess where our balloon vendor lives? He lives in Chilliwack, Columbia. And there's Maxime on the far left with his grown-up daughter who works at his company. And there's a balloon he did, not for us actually. This prototype was for a JPL project, NASA JPL project a while back. But Maxim used to work for Bigelow, if you remember, that were these space hotels that were gonna be these big inflatables. But Bigelow ended up, I guess going bankrupt is the right word. And then now there's a new company he calls Max Space. So later on you can search Max Space and learn about Maxim. There's myself, my husband Charles, and part of our Venus team. We went out we have a place in British Columbia and we brought everyone out while I was on sabbatical. And we drove over the mountains and got to visit Maxim and meet him in person and see the balloon. All right, so remember that was just our prelude because we were supposed to be mulling over, can we ever claim a robust discovery of the signs of life? And by the way, normally when I give a talk, I know that you're not all the public, you're professors and students, but if I give the public talk, I usually don't even go here. It's just like they're exoplanets, there's so many of them, we're looking for gases, we can measure the atmosphere. So this is really like, I wouldn't say like the dirty laundry of the field, but it's something we're really struggling with. We have almost like an existential crisis right now because we wanted to do this for 100 years. We have the telescope now. So how are we going to solve this? So I'm going to, the last kind of small part of my talk is about this. We will have to make incredibly detailed computer models I know like AI is all the thing now, and it's not, it might not solve all our problems, but we need to do the most detailed modeling we can to really know whether or not these the gases are made by Earth. Our field is really complicated. Honestly, this problem is going to be really hard because our Earth is complicated, exoplanets are unknown, there's so many free parameters, but I have no doubt in my mind that we have to embark on this path, and this would take years, decade to be really careful to understand all the physics and chemistry, but this is going to be hard. And you still might not believe us. I'm just listing all my favorite ideas here. Number 2 would be to go and find a true Earth twin. Right now, the planets we can study, and Earth is really out of reach. With this transit method, we're actually limited to what I call an Earth cousin, not an Earth twin. Small planets transiting very small stars. The environments are incredibly different from Earth. But we have plans to do much harder projects where we could go to space and find, try to find the true Earth twin. So NASA has the Habitable Worlds Observatory. One of my favorite projects is Starshade. We have other projects in Europe. Because the thought is that if we could find one that's just like our Earth, that has oceans and continents and a thin atmosphere and a tiny bit of carbon dioxide, it could be easier for us to buy into or explain, if we see oxygen, that we're able to really believe that that's made by life. A third idea is for what we call technosignature gases. It is for pollution. We are polluting our atmosphere. We know about chlorofluorocarbons, for example. Remember earlier in my talk, I was mentioning how life avoids some molecular fragments. Life almost completely avoids fluorine. Fluorine is so electronegative, it is so tightly bound. It is like the superglue of superglues. And if you want to think about it in this simple way I'm trying to explain it, it makes no sense for life to want to use fluorine because it's so tightly on. How can it break it up and then reuse the molecule for something else? So people love this idea of looking for chlorofluorocarbons. We're not there yet because even though we put them in our atmosphere, there's not enough of them. They're not at a high enough abundance for us to really detect from afar. But that's an idea to look for technosignature gases that we would know don't come out of volcanoes. They're not made by, they'd be made by some kind of intelligent life. But what it's really going to take is not just kind of the new space with cheaper rockets and cheaper satellites. It's going to take whole new ideas, actually. So for anyone in the room who's younger than 25, I don't know if there's anyone, this is yours. This is for you, because we're going to need a new paradigm, a new way to get way better data. We might imagine sending star chips, these little tiny idea to send thousands of little space chips to a distant world. It could take, we're ways away from it, even though $100 million was injected into making this project get over some of its tall poles. It is still in the future, but the idea is to accelerate these little solar sails to whip by a nearby star system and to take a picture and send it back to Earth. Another idea, you don't look convinced, but remember, the line is shifting. The other one I really like is the Solar Gravitational Lens Telescope, to send a telescope to 500 times the Earth-Sun distance. So your focal length wouldn't be like this, it would be like 500 astronomical units. And you'd use the sun as a lens to magnify a known background planet and spatially resolve the surface to like 10 square kilometers. So we have our future cut out for us. And to summarize, we are thousands of known exoplanets. The majority today are transiting planets. It's the easiest way that we have to find and study atmospheres. We all saw the graph together. We all saw an exoplanet atmosphere. But what isn't so hard is spotting it. What's hard is interpreting it, is telling how much gas is there and what it all means. And we're on the verge of people finding biosignature gases they might attribute to life, but it's all muddled up in, is the signal real? Is it attributed to the right gas? And most importantly, is it made by life or some other process like volcanoes or something we don't know? So my outlook for you is that we're at an incredibly exciting time. We are the first humans to get to puzzle through all of this. And it's very exciting. But at the same time, this is a generations-long search where it's only just beginning. Well, I hope that I've encouraged you to think outside the box, to try something new. And with the weather clearing today, let me wish you all clear skies.
No, this is for online. Dr. Seager, you earlier mentioned the use of machine learning and AI, and you also mentioned that there's a lot of data out there that is free since it's publicly funded. So what have the results been of AI and ML in studying? I mean, it's a new field. Have there been any notable results?
Well, I'll say that for science, artificial intelligence comes in two categories. One is just to do the job better and faster and with less error. And we do use it to find planets, actually. It saves us time. We have to train it, though, and we often don't have enough training data. Like when people are studying lung cancer and the images, they're having tens of thousands of labeled things. We don't have tens of thousands of planets. And if you have to simulate like a fake planet, you know what? It turns out so hard to simulate fake noise that's real. because the noise we're getting from the star and the instrument is really tricky. So we have that category. And we also have a category where it does something new that we can't do. Like that's where we really want to use AI, where it's not just brute force. And in exoplanets, at least, I've only seen one example there. And that is, there was a ground-based study, and they found like, I don't know, I want to say 50 planet candidates, but they don't have enough resources to follow them all up. They need to know which is most likely a planet before they do the next step. And this person, his name's Jason Dittman, he's now a professor in Florida. He cleverly used a lot of data like the scene, the weather log, things that we humans couldn't necessarily put all together. And he put all these parameters in and trained it on a couple of other like eclipsing binaries and other transits. And it popped out a couple of choices. And one of them ended up being a brand new, really key planet. And there's one final way I'll tell you, it might be a bit too much detail, but we have this class of problems we call it an inverse method. Like those who are in high school or undergrad, you have to invert a matrix. Probably done that. Our equations are too complicated. We can't just write them down and invert them because they're nonlinear. They have like an x squared or they have like an exponential. So we have to do this umbrella class of problems called inverse methods, and they're very hard. They're sometimes ill-posed and our data is really crummy. But machine learning really helps there. It helps us like fill in all of parameter space and not have like discrete values that mess it up. So there's sort of this other space that it's being explored for, which is probably where it'll be most useful. And I just want to say, while we're waiting for the next question, I discovered that my colleague, Kristen Manu here, he used to work mainstream in exoplanets, and now he has switched to AI. He's now a professor teaching students AI in this very fast-moving field.
Hi, I wanted to ask more about Venus. So it's exciting that you've got these plans to go to Venus. And of course, Venus has been a close planet for a long time, but space exploration has largely stayed away because of the harsh conditions and the heat and so on that you hinted at. But can you talk more about the practicalities? You're sending these things into this atmosphere that's so hot, got so much acid, so many things. Like you mentioned something about a space shield, but once you get into balloons and so on, is it feasible, or how do you keep things going in Venus?
Yeah, good question. Let's start with that question of why we haven't gone to Venus for so long. I actually don't think it's all the harsh conditions necessarily. I always think it's been ignored because, you know, scientists studied it. And I mean, I can't speak for the people 4 decades ago, but I literally think they got bored of it. They went so far, but it has so many enduring mysteries. Like remember we were talking about oxygen? It actually has a tiny amount of oxygen, like part per million levels that have never been explained. It has like 10 mysteries like that are just, wow, that just got shelved. And it's true, the surface is too hot and nothing could survive. I really do think the main reason we haven't spent time to go to Venus is Mars. And that's what I like to talk about, the siblings. You know, we have Earth, Venus, Mars. I'm sure some of you have a sibling or you have kids who are siblings. You know how there's that one sibling that gets all the attention? That's Mars, and the one sibling is always ignored, yeah. Now, about sulfuric acid, okay, yes, it is bad. It killed the ant, it kills stuff, but there's a lot of materials that can survive. Teflon, the former Soviet Union sent 2 balloons to Venus, small balloons that lasted on their battery power for a couple of days each. They were just coated in Teflon. And it turns out, if you think about rain, like you can get rained on and not get soaked, right? In some cases. So even if you just sent a probe going through, it's just getting like splattered a little bit. It's not getting like drenched in a way that would like eat away all the metal. But there's plenty of materials that are good. And up in the atmosphere, it's not too hot. It is the right temperature for life. It's definitely survivable. But it gets too hot eventually, and your electronics wouldn't work, and it would be bad.
Other questions?
Yeah, I'm interested in the time scale. How long will it be before we know about life on Venus, which is easily accessible and available, the best exoplanet we have? How long will it be before?
How long it will be? Well, it depends on money. It literally boils down to money, really. And, you know, in astronomy and planetary science, it's a luxury science. So we don't have enough money to go around to all the projects we want to do. But I think if we can get a balloon to Venus with this special instrument that can tell us how complex the molecules are, and, you know, only certain level of complexity is produced just by geology and geophysics and geochemistry, and we can see the complicated molecules, we have a good, not 100%, but we have, let's say, 95%. What we really want to do is do a sample return to bring the cloud material back to Earth and be able to study it up close. But that's probably a few decades, honestly, like by the time we rally resources. But we want to send this balloon mission in 2031. And that's kind of close, but we're lining everything up. We have our partners, we've got the instrument.
Okay, secondary question. If it will take that long to find out about Venus, how long will it take to find out about an exoplanet that we don't have access to? We don't know it. We don't know
Exoplanet,
it.
yeah. Well, there's different levels of belief. What if every planet that is the right temperature for life shows an unusual gas? And let's say there's a time we have half a dozen of those. You might not believe each instance, but maybe there's a case for that there are so many unusual gases, maybe there is a case that there's life there. So I don't think we're gonna have, yes, I'm 100% sure in the next decade, but they're just maybe like growing evidence that it's likely. I think we're on a sliding scale here.
You think they will be easier than Venus?
Well, one thing, I think Venus will be easier because we can go there and say yes or
That's
no.
right.
I for sure think it'll be easier. But when will we know for sure on exoplanets? I mean, I don't want to, that's why I don't like giving this talk anymore, because I used to give the talk and be really excited. I'm like, I don't want to say never, but it's going to take that next generation to find out how to get much better information. But I do think we're going to have candidates. We're going to have lots of maybes. And maybe perhaps there'll be enough maybes that we're all feeling like there's probably life there. But the nuances are hard. We want to get the yes, no, but we're not there.
Let's take one more question here, and then we'll go online, see if there are questions.
Where are these exoplanets? How far away are they?
Good
And-
question.
And what are
Yeah.
you gonna, is it the Webb telescope that's gonna bring back something?
Well, these planets are around, we're searching for planets in our own galaxy, but they're mostly our neighboring stars. So our nearest star system is 4 light years away, and there's a planet there around Proxima Centauri. We can't find all the planets out there. We can only find a subset of them that our instruments are sensitive enough to, but these planets are tens of light years, hundreds of light years. Some of them are like 1,000 light years away. So they're pretty far. I mean, stars are far. Stars are really far away. Now, the James Webb and these other telescopes, we're just looking at them remotely. We're not going there. We're not bringing anything back. We're just doing like remote sensing, where we're just pointing our telescope up and trying to glean all the information that we can. But it's pretty limited.
Let's
Yeah.
go take a couple of questions online, and then we'll come back to you. No question? Okay, go ahead then.
What you mentioned the HWO, the Habitable Worlds Observatory. What tools will that have for remote sensing that JWST doesn't, or what we currently don't have? That's hopefully going to be a game changer, because I think that's the main use case for it, amongst others.
Right. Well, one thing to know is the telescopes take a really long time. They can take decades from concept to launch. And the James Webb Space Telescope was not designed to study exoplanets, because we barely knew exoplanets existed when the James Webb was conceived of. And the James Webb Space Telescope, remember how I told you it's studying the planets that go in front of the star, and we're looking at the atmospheres through this like filtered light? That method itself is very limited to the planets that are edge on, and it's further limited to very small stars, because it's the ratio of the area of the atmosphere compared to the area of the whole star. So what Habitable Worlds will do is it'll go to outer space, and it'll block out the starlight so we can see the planet directly. And in this case, it'll get a different type of star. It's not necessarily going to do a way better job. It's just going to be looking at sun-like stars and true Earth twin planets. And that's what Habitable Worlds Observatory will do that's different.
So a question from online. Hi, Sarah. Glad to see you are making inroads with both exploring Venus and exoplanet research. Are you connecting with the evolutionary biologists working on earliest life on Earth?
Okay, are we connecting with the, not necessarily. It's tricky because we're not trying to, at this point, understand the origin and evolution of hypothetical life on Venus. We're just at the level of trying to demonstrate that biological molecules can survive in sulfuric acid. It is tricky though, because the people that, I want to imagine life on Venus as being the simplest life you can imagine. Like in our bodies, our cells are extremely complex, and there's special proteins that carry special molecules across our cell membrane. But we think that when our life evolved, it was extremely simple, and big molecules could kind of just go through the membrane on their own. And when I imagine life on Venus, I'm thinking of like this super simple life form. But the evolutionary biologists, they always want to think that things have to evolve to something like way more complicated. So yeah, it's a bit of a philosophical disagreement.
Thanks. Just one more from online. How is it that you're able to tell what's in the atmosphere of the transit planets?
How is it that we're able to tell? Well, every molecule has a unique wavelength where it absorbs, actually. And we're able to piece that together because, like carbon dioxide, that's the big one. The one we saw turned out to be carbon dioxide. Most molecules have a unique fingerprint of where they absorb, and we can back out what gases are there. But it's not always so straightforward. Like carbon dioxide, unfortunately, overlaps with carbon monoxide. And sometimes you're really not sure how much of each gas is there. So we piece it together using computer models and measurements in the laboratory and quantum mechanics that tell us what gases absorb at which wavelengths.
Thanks.
Okay, let me ask a question about the hurdle. So I think you told us about the main hurdle you see, which is can I find a specific signature, a line or something that traces a gas that I can be sure, or with confidence I can claim that's from life. There's another hurdle, potentially, I wonder whether you could comment on it, which is that if you go back to the early days of planetary science, if you will, when we were not able to go through the cloud deck on Venus, coming back to Venus, there were serious ideas circulated about maybe there's life just under, because we didn't know how deep the atmosphere was. And so with exoplanets, we're sort of facing as well this as a hurdle. We only see surface layers. We don't know what's going on under. And that actually, is that a hurdle? Do you see that as a hurdle? Or you don't think it's like secondary to the one you highlighted?
Well, I would call it secondary.
Yeah.
It's definitely a hurdle, but I like your point because it highlights how little information we can get. That's like when you're if you fly in an airplane and it's really cloudy, you can't see anything, right? You don't see any land or rivers or cities. And that's what Kristen is getting at, that there can be cases where you miss most of what's there. So it's definitely a hurdle for us, but if we can sense the gases, remember the model can tell us not the reality, but can give us all the realities that are possible.
Including all the different depths then?
Well, it can't tell us what's at the different depths, but it can say here are all the plausible things at the different depths, yes.
Yeah.
So we'll live in a world, it's like a quantum world where for those in physics, like if the wave function, it's all probability. We don't know which one is like real, but we can give you the options.
Okay.
All right, another question. In your studies of exoplanets, not Venus, but exoplanets and different other planets that you've observed, exoplanets that you've observed, are there common gases that you have noticed? Like, I'm sure there's many exoplanets that you've seen. Is there one that stands out above all, and could there be reasons why?
Sure. So for the exoplanet atmospheres, it's not just what gases are common in them, but what are strongly absorbing. Like a skunk spray, you only need a tiny amount for a huge signal. So in these hot giant planets, we are seeing CO2, and that's not the dominant gas. It's not even a dominant form of carbon. It just is so strongly absorbing, it is just seen in pretty much every giant planet. Methane has been discovered as well. And another gas, it just sounds really obscure, but sulfur dioxide kept popping up. And that shouldn't be there because in planets that are mostly hydrogen, you expect all the hydrogenated versions. So you expect H2S, not SO2. And so there's got to be some photochemistry going on that's splitting up molecules that are reforming. So it's mostly CO2, some water vapor, methane, and sulfur dioxide, I'd say. It may seem really obscure, but if you studied this field for 6 months, it would just become normalized for you. Like in that sense, the planets we have most access to, they're hot giant planets and they're too hot for life. They're very puffy, hot atmosphere. So in that case, not signs of life, but they are telling something about the chemistry of the planet atmosphere. And that it's common amongst other ones, yeah. And there's surprising differences too, but I think the whole field is so new. Come back and ask that question in a few years.
So just a couple more from online. First one, if we were on a planet a few hundred light years away from Earth, do you think life on Earth would be detected?
I love that question. Well, with the James Webb Space Telescope, the answer is no, because sun twins can't be accessed right now. If they're going to build Habitable Worlds Observatory, yes, I'd say. Maybe not hundreds of light years, maybe 100 or 200 light years.
Thanks.
Yes.
So the second one, can you explain a bit more about on the Morning Star mission to Venus project that you're working on specifically? The rock that you're throwing to Venus, what's the objective of the project, and how did you decide to develop this rock?
Okay. Well, we want to do a series of missions. And instead of waiting like the decades and having everyone who wants to contribute, we call it here, kind of in a bad way, the Christmas tree approach. Just keep adding things on. We don't want to do that. We want to have a small focused mission. So we had how did we decide on this? We joined forces with Rocket Lab. We call our first mission the Rocket Lab mission to Venus. And we joined forces with Rocket Lab. And we worked together, coming both from science and engineering. Science is what do we want to do? Engineering is what can we do? And we had a couple of instruments. We wanted to send a gas analyzer and look for phosphine and for methane and ammonia. But it turned out with the probe, it was just a bit too complicated to let air flow through because the gas would have to flow through for us to detect. And the CEO of the company, Peter Beck, he got on a call with us and it was pretty clear we had to go for an instrument that was inside and packed away. And so we were more in the space of what can we do? And we really like this idea of probing the cloud particles because that's what we really care about. So our objective is to establish that you can do a mission in a short amount of time. We want to see, our main goal is to confirm or find out that the sulfuric acid droplets in the clouds are not pure sulfuric acid, that there's interesting things in them. And we won't be able to tell you exactly what is in them, but we'll say it's not pure sulfuric acid and has something interesting. That's our main goal of our first mission.
So, thanks.
Wait for the microphone, please. 1 second.
Do you experience any economic pressure or pressure to develop economic uses for the discoveries that you're exploring?
That's a good question. We don't have pressure because society, just like society supports musicians and artists, we get to be like that, narrow category that is just supported for pure exploration. However, sometimes we do come across something, and I just want to briefly tell you about our instrument that's going to Venus. It has heritage from an instrument that went to Venus 4 decades ago. And the person who sent that instrument, his name was Nolenberg, his last name. And he actually made a lot of money off of this because he took the particle, it's like a particle counter almost, because you're sending out light and measuring what comes back. And he made a business at the time in the 80s for counting number of particles in clean rooms as computer chips and other things were starting to get built. And he made this business on these. And it turned out that someone working for him, whose name was Daryl Baumgartner, he made a spin-off business to calibrate them and repair them. And now, many years later, Daryl Baumgartner, he's in his 70s, and he is our instrument builder for our instrument going to Venus. So once in a while we do the mass spec that we plan to take to Venus. It's a really special mass spectrometer. Most mass spectrometers, they have to deposit a charge on the molecule. They fragment it, and it's so fragmented. Like imagine you had a plate you threw against the wall that like putting it back together and understanding what was the original molecule is really hard to do. But this is a really great mass spec. It just so gently puts a little charge on. Now the inventor of that, he did start a business because that would be very valuable. If you could have one of those in your lab, it would be a lot easier. But he couldn't keep all the balls in the air. He couldn't keep that running while he's doing the run. So there are instances where there is a way to get money, but it's hard to do both. And in space engineering, it happens more often because of the commercial space world now. You can invent something at the university, and it's more often they do. Usually it's a PhD student who finishes their PhD and then spins off a company on it. So it is there. We don't usually feel pressure for it, but it happens.
Thanks. You clearly need to get some kind of business going to fund this kind of thing. You mentioned earlier that it's I don't remember your exact words, but it's easier to get hold of a rocket these days than it was. Smaller rockets are available. What does that mean? It's not like you can go to the corner store and, I'll have one of those. So what does that actually mean for your research?
Well, basically, before there were only really big, super custom spacecraft and space missions that you could do. So it would be, you'd need a lot of money and it would take like a lot of time. And by the way, in Canada, really had one of these a number of years ago called MOST, also dubbed the Hubble Space Telescope. But it's the idea of doing something smaller that's really focused. And what happened was literally a revolution in space where people came up with like a form factor. They called it CubeSats. And then industry could come up that could sell you individual parts rather than everything being custom from scratch. So that's one thing. Another thing are smaller rockets. Like the big rockets, literally, it's going to sound absolutely insane, but it's like 50 million, 75 million. But a smaller rocket, like at Rocket Lab, I don't know all the numbers, okay, but it's more like a tenth of that. And so small payloads, small rockets, all the cost gets lowered. And SpaceX having a reusable rocket also lowered the cost as well. So what it means is that just stuff is cheaper, there's more things happening, there's more players, it's more flexible. And that really creates more opportunity.
All right, so another two online questions. Summarize it for the interest of time. So when you're finding life, do you take the biological model of life from the Earth to identify the presence of life on another planet, given that life can have different definitions or descriptions?
Right, well, the great thing about being an astronomer is we can not worry too much about that because we don't have access. Remember, we're not going there unless it's Venus or Mars or another solar system body. We're just assuming that life out there uses chemistry like we do to extract energy from the environment. We eat food, we breathe air, to store energy, and then to release energy. And so we're assuming life uses chemistry. But what exactly that life is it an intelligent humanoid? Is it a bacteria? Does it have a different DNA? Is it totally different? We don't have access to that. We're just, we're just not defining life or thinking of what it's made of, more like what life does, actually.
Thanks. So one last question. While working on a specific exoplanet atmosphere, do we have a abiotic primary, secondary atmosphere as stations according to their star and planetary system formation so that we can focus on anomalies?
Can you just repeat that question?
Yeah, so if we have abiotic, if we know a exoplanet and do we have some sense of what an abiotic atmosphere on it will look like so that we can pick out the biosignatures?
It's really hard to do that. If you ask that question about Earth and imagine Earth being born and giving off gas from its had a magma ocean, like liquid rock that solidified and gave off gas that became in the atmosphere, that would not be our atmosphere today. We got a water ocean, all of our carbon dioxide, most of it went into the ocean. So we're not there yet. We'd love to be able to do that. And maybe remember with the emoticon I had with the exploding head? Maybe there's a world where we can have a model and it can give us all the possible outcomes. And eventually it could kind of self-generate different options for an abiotic atmosphere. But we're very far from being able to do that. We don't know even what the initial inventory of these planets are, and it's super complicated.
Great. One last quick questions, and then we're done.
The word cosmos in Greek means order. So I'm interested in the question of order with respect to exoplanets. And the question is something like, have astronomers extracted any discernible order in the placement of these exoplanets, observationally speaking, or is it completely random as to where these exoplanets are located in terms of our
You mean
perception?
located in space or located
Correct.
in our own?
Located in space.
No order. We think most stars have planets that come out of the gas of dust and disk they're born with, and that the process itself is random. So where something starts clumping up, it then can grow. We think planetary systems formed with too many planets. It's too easy to form, and some got kicked out. Like a game of billiards, they were moving around and just couldn't all be there. So we think it was a very disordered process. and that all planets and almost all stars in space should have a planetary system of some kind.
But and there's a bit of a paradox because I think, based on your presentation, which is very compelling, you're searching for biochemical order within planets, but the corollary to that is that the assertion is that there is no pattern in terms of order, in terms of the positioning of these planets themselves. So how could there be order within the biochemistry composition of these planets and no order amongst the exoplanets themselves?
Do you mean order among the stars with planets or the planets?
The positioning of them in the cosmos.
Yeah, I just think it's, from the scientist's perspective, it's all like rolling the dice. Like a lot of things could happen, and sometimes things do happen, and maybe they appear ordered later, but initially it's just all disordered. It's random, like which stars have what kind of planets. It's random which are in the system. If molecules can come together to make life, we don't know, but we think it's happening somewhere.
Great. Let's have a big thank you for Sara.
That concludes tonight's lecture. Thank you for the thoughtful questions you brought forward. I would like to take this opportunity to tell you about other upcoming lectures. If you like this one, you ain't seen nothing yet, there's more. The F.E.L. Priestley Lecture in History will be given by Professor Matthew Smith from University College London on November 12th, 13th, and 14th, and he'll be talking about his research on 19th and 20th century Haiti and Jamaica. Then there will be the W.J. Alexandra Lecture in English, which will be given by Professor Warren Cariou from the University of Manitoba on November 21st. And his research focuses on the environmental philosophies and oral traditions of Indigenous people in Western Canada, especially in connection with his Métis heritage. Just check the website for event details and registration. These are fantastic opportunities to hear from world-class scholars talking about, as you heard today, the things they are most passionate about. I encourage you to attend, and I hope I will see some of your familiar faces there. Before I close for the evening, let's say thank you to Diana Valencia and Peter Martin for the organizational acumen from the astrophysics in our U of T community, to Kristen Menu and Bo Peng for moderating, and Bonnie Huang for running the hybrid technology. There's a big lot of people out there in the ether. All the students, staff, and faculty involved in planning Professor Seager's visit. It's been a long process. All of you in the audience for providing questions and for attending, and especially you, Sara. Thank you for your inspiring talk. None of us will be looking upwards with the same eyes anymore. For those of you here in person, I invite you to join us for a small reception just next door in our senior common room. Please stay and enjoy some food and drink with us. Good evening.